Hi everyone, it's Rob Brownie here from InsightAcumen. This presentation will discuss and demonstrate a concept model and example analysis for the future Victorian Renewable Energy Terminal at Port of Hastings. First of all, some background to the project. Why is the Renewable Energy Terminal required? Offshore wind is important to Victoria's move to renewable energy. The Victorian Government has set ambitious targets of 2 gigawatts by 2032, 4 gigawatts by 2035, and 9 by 2040. The development of specialised port infrastructure is key to achieving those targets and building a thriving offshore wind sector. No port in Australia is currently suitable to support offshore wind construction, and components for offshore wind are seriously large and place unique requirements on ports, including heavy-duty pavements and significant areas of land. So after an extensive technical review and engagement with key stakeholders, the Port of Hastings was confirmed as the most suitable port facility in Victoria. The area identified for the terminal is the Old Tyab Reclamation Area, OTRA, located within the port area between current users Esso at Long Island Point and BlueScope Steel. The reclamation area site is located within an existing port zone. The terminal is expected to include at least 2 berths with a total wharf length of at least 400 metres and form up to 35 hectares of heavy-duty hardstand, comprised of 10 hectares of reclaimed land, connecting the wharf to the existing 25-hectare reclamation area land. Construction is scheduled to commence in late 2025, subject to obtaining the necessary approvals. The development would see the reclamation area transformed into a multi-user facility with new infrastructure and berths next to the existing shipping channel. So the intent of this slide is just to show the approximate location of the Port of Hastings. In the inset box here, see Melbourne in Victoria, and the Port of Hastings is around about 90 k's southeast by road from Melbourne. And we can also see here that the Port of Hastings is on the western shore of Western Port Bay on the Mornington Peninsula. This diagram also shows the offshore wind zone of Gippsland here, seen between Gippsland and Flinders Island. And these open source references were used along with guesstimates by the model developer, i.e. me. Now to the concept model. Firstly, why? Well, the model relates to the renewable energy sector, so by definition, it's cool and makes a refreshing change from developing models for the non-renewable energy sector. InsightAcumen would love to be involved in the project, and lessons learned from this experience could assist other states and territories in achieving their own renewable energy targets that may include contributions from offshore wind in some cases. The disclaimer, there are always T's and C's, and here are mine. In my case, I do not know boats, that is, I do not know the offshore wind sector or renewable energy terminals, but I have built models testing changes to port infrastructure and the throughput of bulk handling ports. The model of the Port of Hastings terminal is 100% based on open source references. There are loads of assumptions to be discussed later, and the purpose of the analysis is to show the power of what-if type analysis using a discrete event simulation model. The software used was ExtendSim by ImagineThat, version 10.09. I describe it as electronic Lego, where the user starts with a blank canvas and adds blocks from libraries to form processes, connects them appropriately. Then, of course, there's the small matter of programming to make the model fit for purpose. You can read the long list of capabilities, features, and utility of ExtendSim on the slide. For this concept model, the key features will be predicting the course and results of certain actions, identifying problem areas before implementation, exploring potential effects of modifications, and evaluating ideas and identifying inefficiencies. There's some overlap there as well. So in summary, we're going to be conducting discovery experiments and undertaking some what-if type analysis. So this is what ExtendSim looks like. A bit of a general demo here. So we start with building from a blank canvas. Each of the green blocks you can see on the screen here on the canvas from the libraries on the right-hand side. And these are all individual blocks from the item library in this particular case. This is why it looks like electronic Lego. You can just drag blocks, for example, an activity block out onto the canvas, and it will end up looking like this. And then we connect them in clever ways. For example, we have a create block, looks like this here. We have queues. We have a set block, which enables the setting of attributes on items as they move through the model. We have random blocks, which in this case is setting a duration onto this activity block. So an item will be delayed by a random amount set by a distribution in the random block. It will spend that time in this block before moving on. We have merge blocks, we have diverge blocks, and we have information blocks and exit blocks, a whole range of different blocks here. So now I'm just going to start this and you'll be able to see this in action. So as the model runs, you can see entities moving through the model. All these blocks come from libraries as discussed. So I'm just going to give you the laser here so we can point things out. So we're highlighting two blocks here that enable us to set attributes on entities as they enter the model. What's highlighted here is an 85 to 15% pathway split. And the next highlight shows the setting of a duration via a random block. This highlighted section of blocks here show two pathways after a split, where entities spend time in activities. It's followed by a merge and then a 40 to 60% split. So that's fine with animation on, but if we just want the results, we're going to turn animation off and get the results. So with animation off now, these are the results here, which are actually the statistics from the exit block. In this particular case, we have a mean of 2016.3 and a standard deviation of approximately 56. So that is a general model demonstration of ExtendSim. Being a bit more specific then with our model. All right, the scope for the Port of Hastings model. The scope was to build a representation of the Port of Hastings terminal in operation for the offshore wind installation, to model 5 major turbine components, that is monopiles, transition pieces, towers, nacelles, hubs, and blades, to test resupply loads and their frequency, to test installation loads and the frequency with which those events happen. Run the model long enough to install at least 2 gigabytes of turbines offshore, and ensure the model is sufficiently detailed to answer what-if type questions and conduct sensitivity analysis. Also publish the findings on the InsightAcumen website and here where you're watching it on the InsightAcumen YouTube channel. All right, this is an example of the animation that I used in the model when animation is running. So it's very simple animation. I just created some bitmaps to use for more tailored animation. So you can see here the major components of the turbines, nacelles, monopiles, towers, blades, and transition pieces, all are represented in this particular way. The unloaded transport for those 5 components are represented this particular way. When those transports are loaded with the components, they look like these in the model. And then we have the ship representations. This is what an installation ship unloaded looks like. This is what a loaded installation ship looks like. When this installation ship is jacked, in the offshore wind zone for installation, it looks like this. And then a resupply ship is at the bottom right there. Oh, once again, here's a picture of the Port of Hastings. And what this slide shows is an overhead from Google Maps of the Port of Hastings area, where I've overlaid my own terminal pavement area in grey. You can see that area in grey there. So this is the old Tyab reclamation area, and I've also added space for 2 berths, a resupply berth here and an installation berth. This grey area should be approximately 35 hectares. There are storage areas for the 5 turbine components, nacelles, monopiles, towers, blades, and the transition pieces. We have places for, pardon me, for the ground transport to wait. You'll see more of that once we have the engine running. So this is the ground transport for the monopiles, and this is a ground transport for towers. We also have berthside areas for loading for the installation ships and for unloading for the resupply ships. Now to the assumptions and constraints. There are a large number of these, so please bear with us while we just work through these. 1 wind turbine or 1 set equals 1 monopile plus 1 transition piece plus 1 tower plus 1 nacelle hub plus 3 hubs, plus 3 blades. The starting inventory at the port, so in the yard, 21 sets. That is 21 bits that make up 21 sets of bits that make up 21 wind turbines. The yard capacity is effectively infinite, but we don't have infinite animation, but we do have infinite capacity for the purpose of the model. We have 1 resupply ship and 2 installation ships conducting events. We have separate berths for resupply and installation ships, which I showed you in the previous slide. We have separate ground transporter resources per component. Very basic business rules for unloading and loading. The resupply ship unloading and the installation ship loading can occur at the same time at their different berths. Installation ships have the same number of components in constant loads for each trip to their offshore installation area, and components for the installation ship load will start being transported from the storage yard as soon as ship arrives. But wait, there's more. Installation ships load in this order. They will start with monopiles, then transition pieces, then towers, then nacelles hubs, then blades. In no particular order, but that's simply how I've done it in the model. Resupply ships are not modeled in any significant detail. They have a constant number of sets for each resupply trip, and those ships will unload in a similar order. So they will unload monopiles, then transition pieces, then towers, then nacelles hubs, and then blades. The operations are 24/7, 365. Durations are constant. That is, there are no probability distributions to represent any range of values. There's no planned maintenance. There are no breakdowns. So mean time between failure, MTBF, and mean time to repair, MTTR, are not applicable in this concept model. There are no planned shutdowns, i.e. yard-wide shutdowns to discuss safety or anything of that nature. The potential impact of maintenance, breakdowns, shutdowns on operations, those potential impacts are not modelled. The potential impact of weather on operations is not modelled. The potential impact of tides on operations, but could be. All of these could be. The potential impact of maritime or port traffic on operations is not modelled. Personnel are not specifically modelled. Turbines are up to 18 megawatts with fixed foundations, and there's a reference there. In the model, we're using 18 megawatts per turbine. The duration of the model run is 2 years from 2029 to 2031. It's very easy to change and or increase that year range in order to model additional port operations. All right, now we're going to check out the version of the Port of Hastings terminal model that I used as a baseline. Here's the configuration. The runtime is 2 years, as we mentioned a sec ago. The resupply ship inter-arrival time is 10 days. The ground unload time per component piece for resupply ship, 20 minutes. The ground load time per component piece for installation, 20 minutes. The ground transport time per unloaded component piece on the resupply side, 20 minutes. The ground transport time per loaded component piece on the installation ship side, 20 minutes. And the installation ship time on jacks in the offshore wind zone is going to be 4 days for installation. So this is baseline. All right, and now we're going to have a look at the baseline model variant running. So I've just started it running there. So you can see the turbine components in the yard. A monopile was just transported. You can see it on its transporter there. The transporter is now unloaded and back in the yard. So these transporters are available for both the unload or resupply and the loading of installation ships. So you can see we have an installation ship at berth for loading, and there's a resupply ship at berth for unloading. So components are already being unloaded from the resupply ship and placed in this area, ready to be transported to the yard. Components are being transported from the yard to the installation staging area here, ready for loading onto the installation ship. Transporters returned back to the yard when the current task is complete, ready for their next task. Loading of installation ship and unloading of resupply ship, they can occur at the same time. When a resupply ship is fully unloaded, it will leave the berth until another resupply event occurs. When the installation ship is fully loaded, it will leave the berth for the offshore wind zone to commence installation, then return to port ready for another loading event. This process will continue until end sim. By end sim, we have the key metrics we want for the what-if analysis that we're undertaking. If animation remained on, it would take a long time to achieve the results that we want, and that might deprive you of the will to live if you just let it run with animation on, despite it looking super cool. So animation is very useful for debugging from a model developer perspective, and also good for stakeholders to see what's going on at a high level. However, in order to get results faster, all results that we're going to see shortly were achieved with running the model with animation off. So now we're going to move to the next slide to check the results. And here are the baseline results. So the key measures for analysis are in the table here, where we have the number of turbines installed, the gigawatts installed, the number of installation ship completed events, number of resupply ship completed events, and the final 7 figures here are utilization figures for the installation and resupply berths, and then the transport for the 5 major turbine set components. In addition here for the baseline, we're just noting here that the steady state unload duration for resupply was between 9.9 and 10.8 hours. The at berth duration for the resupply was between 13.4 and 14.3 hours. On the installation ship side, the steady state load duration, 23.5 hours, and their time at berth was 26 hours. So we have 4 questions for our analysis. Let's have a look at those. So the 4 questions were, the first one, in the baseline model, resupply ships have an inter-arrival time of 10 days. If the system is left to run without any new constraints, what is the impact on the throughput, that is, turbines installed, if the inter-arrival time is reduced to 8, 6, and 4 days, or increased to 12, 14, and 16 days? Question 2, what is the impact on throughput, number of turbines installed, of reducing the ground unload and load time per component by 20%? Question 3 is similar, but reducing the ground transport time per component piece by 20%. What happens then? We'll be able to check it out. Question 4, the baseline model currently uses a 4-day interval for time spent jacked up in the offshore wind zone, the maritime ops area, undertaking turbine installation. So what would be the impact on throughput if the installation crews were able to complete their operations per trip more efficiently by spending 3.5 days jacked instead of 4 days? Would it impact on the key metrics if time and operations area increased? So we're going to test and analyze that one question at a time. So analysis question 1, where we're just adjusting the interarrival time for the resupply ships. And the configuration, so in red there is the change that we're making, just adjusting the interarrival time. And these are the results. So this chart has interarrival time for the resupply ship on the x-axis. This is the baseline here at 10 days. And we have the number of turbines installed on the y-axis. So note here that the baseline we have 156 turbines installed across the 2 years of runtime. Also of note here, note the non-linear relationship between the resupply ship interarrival time and the number of turbines installed. That I thought was quite interesting. So this is gigawatts installed, and the shape is identical to the last slide because there's just a constant factor multiplier between the two. So the difference here is we have gigawatts installed on the y-axis rather than number of turbines. So as per the previous chart, we have a non-linear relationship between resupply ship interarrival time and the gigawatts installed. In this particular chart, we have number of installation ship completed events and number of resupply ship completed events. We have the interarrival time as per usual on the x-axis and those events on the y-axis. We have installation ship in blue and resupply ship in red. So as interarrival time reduces, so as we head this way on our chart, then obviously resupply ship events are more frequent. And as we get more resupply events in red here, then that allows for a greater number of components to be in inventory in the yard, and therefore for more installation ships to be loaded and installation events to be completed. And once again, note the non-linear relationship to the two plots. This particular chart shows ship berth and ground transport utilization. The two berths are at the top of the chart in the red and the blue, while the transport for the 5 turbine components are the lower 5 plots, although you can only really see 3 because we have an overlap between the transition piece, the tower, and the nacelle hub utilization. So under the orange line, we actually have 3 and 1 there. As expected, both resupply and installation berths are busier when the resupply ship interarrival time reduces. So at this end of the chart, and of course, vice versa. So for the second question, what is the impact on throughput when we reduce the ground unload load time per component piece by 20%? So change from the baseline in red. So we are reducing the unload time that started at 20 minutes by 20%, which means that the time is down from 20 minutes to 16, and similar for the load time on the installation side, that reduces by 20% from 20 minutes to 16 minutes. So everything else is as per baseline. This is the only changes. So what happens here? So these are the results. The results show that there are minor insignificant changes only to some of the utilization metrics. We have a change to the installation berth, very small, and we also have a change to the blade transport utilization. just very minor changes. And that was it for that one. So to analysis question 3, what is the impact on the throughput if we reduce the ground transport time per component piece by 20%? For the configuration changes in red, we reduce times on the resupply side from 20 minutes down to 16 minutes. And on the installation, we also reduced it from 20 minutes to 16 minutes. Everything else as per baseline. And these are the results. The results, once again, similar to the last one, show that there are just minor insignificant changes to some of the utilization metrics. You can see the number of turbines, the gigawatts, the number of ship events are very similar. We have one additional resupply ship event, and then minor changes only to several of the utilization numbers. And now to question 4. So in this particular case, the baseline uses a 4-day interval for time spent jacked up. So what would be the impact if that was reduced? And also we should look at also what happens if it increases. What impact does that have? So for configuration, the change from baseline is the installation time spent on jacks is going to be reduced to 3.5 days. So what would it impact on key metrics if the time in ops area increased? We're going to look at that as well. So here are the results and analysis for that. On the x-axis, we have the installation time in the offshore wind zone with baseline here at 4 days. On the y1 axis, left-hand side, we have number of turbines installed. On the y2 axis, right-hand side, we have the number of turbine sets left in the inventory in the storage yard at the terminal. So this is the baseline at 4 days, spent on jacks in the offshore wind zone, and 156 turbines installed. So the first change we wanted to test was to test the reduction of 4 days spent on jacks to 3.5 days spent on jacks. So you can see that there is no change to the system. We still have 156 turbines installed and 3 sets left in inventory at the yard at the Port of Hastings. So with no change on the reduction side, then we looked at increasing the time spent on jacks. So we then incrementally increased the installation time to 10 days, no change, 15 days, no change, 20 days, no change, 25, same, 30, same, 35, same. Then after 35, we get an interesting change. From this point, the number of turbines installed steadily decreases in the blue here, while there is a significant increase in red here in the number of sets left in inventory in the yard. So this type of what-if analysis shows the power of simulation, because it would have been far tougher to predict the shape of this chart without a model where a test and new results can be achieved literally within seconds. So next steps for me: to keep informed by further implementation statements from the Victorian Government and remain engaged with the engagement team. If engaged by subject matter experts or the Port of Hastings, many of the assumptions made could be modelled robustly using known values, probability distributions, or by SME professional judgment. Expert advice would be needed in order to make a model that is fit for purpose for the Port of Hastings or any other renewable energy terminal. So for SME advice, professional judgment, which would be required in order to make a robust model, considerations for them and advice that I might be asking about include physical layout, so preferences, configurations, build and installation schedule, if applicable, ship numbers, requirements, limitations on both installation and resupply. For infrastructure, what are the numbers of widgets or bits to support the operations, deconfliction, staging points, and business rules. Personnel, numbers, attributes, shifts, and of course business rules associated with personnel. On the processing or activity side, where are the queues, where are the buffers, what are the durations, and are there probability distributions to support those durations. For equipment, reliability and maintainability, is that data available? Should we model it? Capacity, what is the inventory? What is the storage? Where are the bottlenecks, or where do the experts think bottlenecks may occur, so that we can focus in and have a look at those particular areas as a matter of priority. For the weather, what's the probability, likelihood, severity, and impacts? On tides, what's the schedule? What are the ship requirements for certain tides? They might change depending on the size of vessels. And what are the impacts of those tides? For model validation, what is the methodology we should use? Have similar builds been made? And do you, the SMEs, have data that we can use to validate the model, to then trust it so that we can go forward and test possible futures? All right, this is an InsightAcumen slide, so feel free to contact me via email or on LinkedIn. So for the Victorian Renewable Energy Terminal, so this was my presentation on a concept model for the future terminal at the Port of Hastings. A PDF version of this presentation will be available on the InsightAcumen website under case studies and articles. And thanks very much for watching.